So good evening everyone. I'll start today's class. Before I start today's class, I'll give a quick recap of what I had discussed in the last class, and then we'll be starting with today's class. So last class we were basically discussing about regression. So we discussed about mostly about linear regression. How do you fit a straight line to a set of data which is given to you? Suppose you perform an experiment and you get a set of data of x and y variables. First, you need to understand which is your independent variable and which is your dependent variable. Then you need to proceed to find what kind of relation does that independent variable have with the dependent variable. So first of all, you plot the data on your graph sheet or using any software, you plot your data, just the data points, a scatter plot you plot, and try to understand which relation can best fit your data. So if it is a linear, you see a linear relationship that is a straight line between the dependent and the independent variable, then we perform the what is called the linear regression. And also, I also discussed about how to linearize a non-linear data. If you have a set of non-linear data, that is, suppose an exponential set of data or any other kind of data, which does not hold a linear relationship between the independent and the dependent variable, then also you have a provision to linearize the data by manipulating that particular equation. I discussed all those things in detail. I'll just give a quick recap. So, so how good is your fit or how good is your linear regression? That is basically denoted by a factor which is known as the correlation coefficient. So if your correlation coefficient is close to 1, that means your fit is very accurate. If the more it deviates from 1, less accurate is your fit. So if your y, that is the dependent variable, it increases with the increase in the independent variable, then we say that x and y hold a positive correlation because our r value is greater than 1. So that is a convention which we generally hold. If our y decreases with the increase in x, then we have a negative correlation and value of r is less than 1. Okay. So now what is the basic algorithm to find out? We first of all, as I discussed, we prepare a scatter plot from your experimental data. That is, you tabulate your experimental data. And then if you are going with a linear fit, you draw a straight line along the plot. Suppose here these red dots are my data points, and I want to fit a straight line to this data through these data points. So you can see here all these 4 points, we cannot fit a single straight line which will pass through all these points. So you have multiple possibilities of drawing a straight line which passes through most of these points. Then so here I have drawn two lines. One is L1, that is the blue curve, and one is the green dotted line, which is L2. So there are two straight lines basically which describes your plot here. One more straight line you can draw. Infinite number of lines you can draw between L1 and L2. So now you need to understand which is your line of best fit. So how do you do that? So to understand that, here I have drawn, say these blue points are your data points, and two lines I have drawn, L1 and L2. Suppose the equation of L2 is y equal to a2 plus a3x, and the equation of line L1 is y equals to a0 plus a1x. Now you try to find out at each value of x1, as I have shown here from x1 to x7, what is the predicted value using that straight line, and what is the value which you have got from your experiment. Then you find the difference between, then you tabulate all this. So you make one column of x, which is x1 to x7. Then what is the predicted value of y from line L1? So it is basically for x1 it is a0 plus a1 x1, x2 it is a0 plus a2 x2. Like that you find out all the values of y predicted by L1. Similarly, you find out the values predicted by y L2. Then you know your actual y's, that is the plot, the data points. So you have y1, y2, y3. Then you find out the error or the difference between the values predicted by L1 and L2 and your actual value. So there will be two sets of error. That is, one is the set of errors for line L1, that is given by EL1, and another set of error which is given by line L2, which is EL2. So then you find out the cumulative error. So here cumulative error, we do not sum up all the errors because Suppose, as I have shown here, some errors might be positive and some errors might be negative. So if you just sum up all the individual errors, then your total error might sum equal to 0. So that's why what we do is we basically take a modulus of each of the errors and then we sum. Because if we do not do that, there can be positive errors as well as negative errors, right? So that positive errors and negative errors can sum up to 0, which is not correct. So your error basically is mod of y true, that is the actual value, minus the predicted value using the line equation. Similarly, another form of error also we can think of. This is one concept of cumulative error. Another cumulative error is this equation. The second equation which I have marked here. It is basically the sum of the squares of the errors. So we take individual errors and square it and then sum up. So this basically gives a clearer picture of the error, and that's why we use this convention as the actual error. So what was our aim here? Basically, we were given with a set of x values and set of y values. We need to find the best line of fit. So how do we do that? Our best line of fit, we do not know what is a naught and a1. We basically have to find the best line of fit. That means we have to find the equation of the best line of fit, right? So for the equation, you need basically two variables, the slope of the line and the y-intercept of the line. Then you can get the equation y equal to mx plus c or a1x plus a naught here. So as I told you, for the best line of fit, your error should be minimum. So our target should be to minimize this E. Okay. So we know from calculus that at the point of maxima or minima, your derivative of the differentiation of the function with respect to the variable should be 0. So we do it here. We apply that concept here. We find out the partial derivative of E first with respect to a naught and equate it to 0. Similarly, we find the partial derivative of a1 with respect to of E with respect to a1 and equate it to 0. If we do this, then we can, I have not done the derivation here, it will be a long one. So if we do this, we will get two formulas for a naught and a1. A naught is the y-intercept of the line and a1 is the this slope of the line. So it is in terms of the summation of the dependent and the independent variables. I hope this is clear to you. Is it clear? Any doubts? Any doubts, anyone? Am I audible? Okay, so now we will talk about the next phase of the class here, the last class what we talked about. Okay, Javed, it's fine. Okay, you can type in the chat section. Fine, no issues. It is clear, right? Any doubts, you can just type in the chat section. Okay, so now suppose you have a set of data which basically doesn't hold a linear relationship. Suppose so what you want to do using this equation of to find the regression coefficients of a0 and a1, we need to have the only constant here is the relationship between x and y should be linear, right? So if you have a non-linear data, what we do is we try to manipulate that equation and express it in some way as a linear data. So here, as we have seen here, we have an exponential data. So the relation between x and y is here exponential, which is given by y equal to a e power bx. So if we just manipulate this data, if we just do some simplifications of this equation, we can see that it turns out to be a linear form data. which is ln y equal to ln a plus bx. So if we take this ln y as the new dependent variable as y dashed, and we can see that it has a linear relationship, right? So now in this we can apply the previous formula and we can get the values of the coefficients, that is a and b here. Similarly, if we have a inverse relationship like this, y equals to x upon ax plus b, here also we can manipulate it and we can get a linear relationship between the, if we just change the variables, the dependent and the independent variables, if we change a bit, then we can easily get a linear relationship between x dash and y dash. So, okay. So this is, if you need to remember the formulas for A naught and A1 every time you perform this method. So if you don't want to remember that, you have to go through the matrix approach. So in the matrix approach, that basically gives me a generalized technique for finding the coefficients here. So suppose you have a set of data which is x1, y1, x2, y2 up to xn, yn. So you have y1 to yn, which is given by y1 is a naught plus a1 x1. Similarly, y2 is a naught plus a1 x2. Like that, up to yn you have a naught plus a1 xn. So if you write this equation in the form of a matrix, so you can write y as a column vector, y1, y2 up to yn. The size of that vector is basically n cross 1. And this x matrix we can write like this, n cross 2 matrix, 1 x1, 1 x2 up to 1 xn. And we need to find out our coefficient matrix, which is the which we are taking as phi here. So if we multiply x and phi here for this one, we will get y. So the relationship is basically y equals to x into phi. From this we need to find out phi. So what we do basically is, if we have a normal situation, we take the inverse of x and multiply it with y. So if we have y equal to x phi, we basically find out phi by x inverse into y. But here the problem is this X matrix, if you see, it is not a square matrix, it is a rectangular matrix. So that's why finding the inverse of a rectangular matrix is not possible. So we need to find some other way to find out this phi. So what we do is, we need to understand that any rectangular matrix or a non-square matrix, that can be converted to a square matrix by if we multiply that matrix with the transpose of that matrix. Suppose you have a matrix of the order say m cross n, and this is not square matrix, okay? M and n are different. So if you multiply it with the transpose of the matrix, what is the order of the transpose of the matrix? It is n cross n. If you multiply these two, you will get m cross n, always. So basically, in order to convert a rectangular matrix into a square matrix, you have to multiply it with the transpose of that matrix. So what we do is, on both sides of the equation, we multiply with the transpose of x. So it gives x transpose y equal to x transpose into x into phi. So from this we can find out phi, which is x transpose x inverse multiplied by x transpose y. So that will give me the phi. So any regression, if you linear regression, if you want to perform using the your MATLAB code, I have not shown the MATLAB code for this because this is very obvious. So if you want to perform through MATLAB, if you have a more set of data, you can't perform a hand calculation, you can obviously always use this equation to find out the this value of phi here, the coefficients. So then we, using that equations, we basically did two examples to find out how we do that. So this is all about the regression. Today we will start a new topic which is called interpolation. So first you need to understand what is the meaning of interpolation, then we will go into the details. So suppose I'll just try to, suppose you have x here, if you have y here. So what we, so first we try to understand the basic difference between your regression and your interpolation. Suppose you have a data set like this. Suppose you have a data set like this. So if I ask you to fit a linear straight line, to this data, what we will do is, we will try to draw something like this, or wherever the error is less, we will try to draw through this or this line, or we'll try to draw like this. So this will be my most accurate line, I think. This is the line of best fit. So here you can understand that your straight line will not pass through all the points. It will basically pass through it will be passing through most of the points, but it will not pass through all the points. Now, if I have to do a interpolation, suppose you have the same set of data, say, what we do is we just trace the data points. We do not see what is the line of best fit or something like that. We basically test. We basically trace the data points and so this is my interpolating curve. So the main difference between a line of regression and an interpolating curve or interpolating polynomial is that in regression your line of best fit that passes through most of the point, or it best mimics your data. It doesn't exactly represent what your data set is. But in interpolation, the interpolating curve exactly traces your data, and uh, it exactly passes through all the data points. So that is the basic difference between regression and interpolation. So I'll just write it down. In regression, it is the line that best mimics the data. And here it is the curve that traces all the data points. So an interpolating polynomial or an interpolating curve, it is a curve that traces all the data points, right? Now another thing we need to understand, that is the difference between interpolation and extrapolation. The difference between interpolation and extrapolation. So what is the difference between interpolation and extrapolation? So suppose I'm telling you, you are given a set of data points and you want to find the interpolating polynomial between them. Suppose there are data points like this. Suppose you have a data points like this. So what I do is, as I told you, I join all these data points. I trace all these data. So suppose this is your, say, x1, and your this one is, say, some xn. So you will get an equation of y in terms of x, right? So y will be some f of x. Now this function is valid only for x belonging to x1 to xn. Only for x belonging to x1 to xn. Suppose if you take a point somewhere outside this range xn, and you say that, suppose here you take some point, say xn plus 2, and you say that this is, so you extend this one and you say this is my functional value. That is not correct, because your interpolating polynomial is only valid within the range of the data points. And the difference with extrapolation is valid even outside the range. So we don't have any information outside the range. Whereas in extrapolation, what we have is extrapolation is used to find an unknown value of y for an unknown value of x. Suppose you have the same data points, say like this. You have some data points like this. You join them and you say that suppose I have performed the experiment for x1 till here it is say xn, and I want the value of the function, what will be my value of the dependent variable at some other point. Say we say at here. So what we do is basically we extend the curve. That is what is meant by extrapolation. We extrapolate our curve and we find out the functional value of at this point, say xn plus 2. So here it predict values outside the range. So I'll give you an example with suppose you do an experiment, anything you suppose in electrical engineering, if we do many experiments, right? So I'll take the basic Ohm's law experiment if you do. So what you do is basically you for different values of current you take the voltmeter readings, right? So suppose I have taken my readings for say from 1 ampere, 1 milliampere to 5 milliampere. You have a set of voltage values. So suppose I am taking V and I here and you have a set of values. Say you have done your experiment for 5 values, 1 milliampere, 2 milliampere current, 3 milliampere, 4 milliampere and 5 milliampere. Suppose you have got your voltage here as 10 volts, here as say, you will not get exactly V equals to I here, right? So here you say 29.5 volts, here 38 volts and here some 49.5 volts. So now I tell you to find out, you have done the experiment up to 1 to 5 milliampere. If I tell you to find an interpolating polynomial, that polynomial will give you your values within this range 1 to 5 milliampere. Any value in between that it will correctly predict. But if I tell you extrapolate it and find the value at say 8 milliampere. So what you do, you plot this V and I curve, something like this. You will get some plot like this, and you then extend this curve to find out what is my 8 milliamp value at 8 milliamperes. So that will be extrapolation. We basically extend the curve outside our range to find out what is the unknown value of y at a different value of x for which we do not have the data for that, or we have not performed the experiment for that. So this is the difference between interpolation and extrapolation. I hope it is clear to you. Any confusions, anyone? Any confusion, anyone? Is it clear, everyone? Can someone respond? Is my voice audible?
Yes, sir.
Okay. Is it clear? It's clear, right, Maruf?
Yes, sir.
Okay, fine. So then I'll move to the next topic of today. So we'll first see Newton's interpolation formula. So before that, we will see a basic of the interpolation. So what we do in interpolation is we try to suppose we try to fit a polynomial we try to fit a polynomial of degree n to a set of n plus 1 data. So suppose you have 10 data points. So using those 10 data points, I can fit it to a polynomial, at most to a polynomial of degree 9. Because you have 10 data points, you will have 10 equations, 9 equations from them. And from that, we can only fit a polynomial of degree n. That is one less from the number of data points. So this polynomial will pass through all the data points exactly. So there is no approximation here or error concept here. So your polynomial will pass through all the data points exactly. So there are many interpolating polynomial formulas which are available. We'll see some of them. First one is the Newton's interpolating polynomial. So here your your values of the dependent variable y will be known at equispaced values of x. At different values of x, your value of y will be given to you. That is here the space between the consecutive values of x are equal. That is, we have equispaced values of x. So here we have a concept of forward difference, backward difference, and central difference. First, we will see with forward difference. Okay. So what is the concept of forward difference? So your forward difference is of yi is given by the difference between the next y value and the current y value. Yi, which is the difference between the next y value and the current y value. Suppose you have 4 data points. Suppose you have x and y here, 1, 2, 3, 4. For this, you have say 10, 20, 30, 40. So if I tell you to find out delta y4, it will be basically 40 minus 30. If I tell you to find out delta y3, 30 minus 20. Okay. So since we are going in the forward direction, it is known as forward difference, right? And similarly, for the dependent variable also, independent variable, sorry, it is xi plus 1 minus xi. So this is the first order forward difference. This is first order forward difference. So we also have second order or higher order forward differences. So what are the higher order forward differences? So here second order forward difference will be given by del square yi. So what is del square yi? It is del of del yi, right? So what is del yi? From the previous expression we can write del yi is basically yi plus 1 minus yi. So this basically gives me equals to del yi plus 1 minus del yi. So if we further simplify, del yi plus 1 will be yi plus 2 minus yi plus 1, and del yi is yi plus 1 minus yi. So del square yi basically that transforms to yi plus 2 minus 2yi plus 1 plus yi. So this is your higher order difference. So now based on this, we need to form a generalized formula for your nth order higher order forward difference. So how do we do that? If you have del j of yi, so it is basically, if you see this equation here, del square yi is del of del yi, that is del yi plus 1 minus del yi, right? So it is basically del j minus 1 of yi plus 1 minus del j minus 1 of yi. So this is the formula. If you want to find out third order or fourth order difference, you cannot go on doing like first order first, then second, then third, then fourth, as I did here. So you can use this to find out higher order differences. Higher order forward differences. So one more concept we use here just for easiness of calculation here. Up to this, is it clear? Any doubts? Any doubts, Maruf, Javed?
No, sir.
Okay. So next we have what is called the variable transformation. Okay, we'll see this later. We'll not. Okay. In variable transformation, so we have our, as I told you, del xi. What is del xi? It is xi plus 1 minus xi, right? So we use a variable alpha to represent this x minus x naught by del x. So x we can basically represent as x naught plus alpha delta x. We use this variable transformation in order to simplify our calculation. I'll show you how it will simplify our calculation. So, okay. So we have the divided differences, everything we have it now. Now we need to how we are going to use these divided differences in forming the interpolating polynomial, right? So we have here the interpolating polynomial of degree n represented by Pn of x. So it is basically, we represent it like this. So it can be represented as say a naught plus a1 into x1 minus x naught, a2 into x, sorry, is a1 into x minus x naught. Then we have a2 into x minus x naught into x minus x1 plus a3 into x minus x naught, x minus x1, x minus x2. Like this, we'll have up to n terms, right? So it will be basically an into x minus x naught minus x1 dot 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 up to x minus xn minus 1. One value less, right? So if this is my polynomial, we need to find out this polynomial. So in this polynomial, we have to find out these coefficients. That is a naught, a1, a2, a3 up to an. We have to find this out. If we can find this, our job is done, right? Then we can easily, we know the values of x naught, x1, the tabulated values, then we can easily find out. So how can we find out it? So what you know here, so you know at value of x naught, your value of y is y naught. Similarly, at value of x1, your value is y1. So we'll use that here. So you substitute in this equation x equals to x naught. So if you substitute x equals to x naught, the value of your polynomial Pn of x, that is basically equal to y naught. Similarly, at x equal to x1, your Pn of x is y1. So we do this. First, we substitute x equals to x naught. So your left hand side is y naught. It is basically y naught equals to a naught plus. So all these remaining terms, if you substitute x equals to x naught, one term is always there, which is x minus x naught. So that will basically cancel. So all other terms will be 0. So your a naught will be given by y naught. So you have found out one coefficient. A naught is given by y naught. Now you substitute the next one, that is x equals to x1. That is, then y will be equals to y1. So it is basically y1 equals to a naught plus a1 into x1 minus x naught, and remaining all other terms will be 0 because we have x minus x1 here. So from this we can find out A1. What is A1? Y1. Again A0 is Y0. We can substitute that. Y1 minus Y0 by X1 minus X0. So what is Y1 minus Y0? It is basically del Y0. From the forward difference formula we can write del Y0 upon X1 minus X0. X1 minus X0 means X0 is the first value of X, X1 is the second value of X. So the difference between two consecutive value of X is basically delta X. That is del X. Clear? Now we have got A1. We'll just find one more value of the coefficient and then we'll try to generalize it. Okay. So what is Y2? Y2 will be again A0 plus A1 X2 minus X0 plus A2 into X2 minus X0. All other terms will be 0. So now if you simplify this one, A0 we substitute as Y0. A1 we substitute what we got, delta Y0 by del X into X2 minus X0 plus. So what is X2 minus X0? X0, X1, X2. So the gap is between consecutive values, it is delta X. So X2 minus X0 will be 2 delta X. And X2 minus X1 will be delta X. This is nothing but mathematical manipulations what I am doing. So if you simplify this further, Y2 equal to Y0 plus the Y0 by delta X. Again, X2 minus X0 we substitute here 2 delta X plus 2 delta X square into A2. So if we just find out y A2, it is Y2 minus Y0. So del X cancels here. 2 delta Y0 upon 2 delta X square. So this delta Y0 we just replace this Y2 minus Y1 minus. So what is delta Y0? Again it is Y1 minus Y0. 1 second. Sorry, it is Y2 minus Y0 here. So if you substitute this, A2 is basically Y2 minus 2Y1 plus Y0 by 2 delta X square. So what is Y2 minus 2Y1 plus Y0? We have just seen here, right? The second order forward difference. If we substitute here del square Y0, what is it? Y2 minus 2Y1 plus Y0. So here in place of Y2 minus 2Y1 plus Y0, we can write A2 will be equal to del square Y0 by 2 del X square. And what this is your A0, A2, sorry. Then what was my A1? A1 was delta Y0 by delta X. Okay. So, and A0 was only Y0. So if we try to generalize this and we try to find out what is AN, that is the nth coefficient, what it turns out to be, it basically turns out to be del power n Y0. Then you have n factorial into del x power n. So this is my formula from the Newton divided difference. It is del nth order forward difference of Y0. Then we have n upon n factorial into del x power n. Is it clear? Any difficulties to understand? Just 5 minutes. I'll just come back. Okay, so we'll continue. So here we have found out the the coefficients of the polynomial of an nth degree polynomial to fit a set of n plus 1 data. So that's it. So now we need to if we want to we have to substitute these values in the actual polynomial, right? So for that, what was our polynomial? It was basically Pn of x is a naught plus a1 x1 minus x naught plus a2 into x, sorry, it is x minus x naught, a2 into x minus x naught into x minus x1, a3 into x minus x naught, x minus x1, x minus x2, and up to n terms, an x minus x naught, x minus x1, dot dot dot, x minus xn minus 1. So we have n minus 1 data, and to it we have fitted a nth degree polynomial. Okay, so now we if we this a naught, a1, a2, we need to substitute in these equations. So you can understand, if we substitute these equations there, that equation will become very complicated. So what we do is we do a simple variable transformation. So what we do is we replace x as x naught plus alpha delta x. We introduce a new variable which is alpha. So here it is. So what will be x minus x naught? It will be basically alpha delta x. Then again, if we try to find out what is x minus x naught upon delta x, it will be alpha, right? Again, if we want to find out x minus x1, so what is x minus x1 upon delta x? So x minus x1 is x naught plus delta x, right? So it is basically x minus x naught upon delta x minus 1. So x minus x naught upon delta x is again alpha, alpha minus 1. Similarly, like this, if we try to find out x minus xk upon delta x, it will be alpha minus k. So if we do this simple variable transformation and then we substitute it, so what is Pn of x? So here I am substituting a naught is y naught. What is a1? A1 is delta y naught by delta x into x minus x naught. Then your a2 is del square y naught upon 2 factorial into, what was it? Delta x square into x minus x naught, x minus x1. So like this, we have up to nth term, right? Del power n y naught upon n factorial x power n, x minus x naught dot 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 up to x minus xn minus 1. If we now substitute this change in variables, so it is y naught plus this x minus x naught by delta x, that is basically alpha, right? Alpha into delta y naught. Again here, if you substitute this, here it is x minus x naught into x in the second term, x minus x naught and x minus x1 upon delta x square. So you can just change it like this, x minus x naught by delta x and x minus x1 by delta x. Again, your x minus x naught by delta x is alpha, x minus x1 by delta x is alpha into alpha minus 1. 1 to del square y naught by 2 factorial. And if you just do this, it is del power n y naught n factorial x power n into alpha minus 1 dot 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 alpha into alpha minus n plus 1. So your final generalized formula from this, it comes out to be y naught alpha delta y naught plus alpha into alpha minus 1 by 2 del square y naught by 2 factorial del x square plus dot dot plus alpha into alpha minus 1 into alpha minus 2 dot alpha minus n minus 1 into del power n y naught by n factorial delta x power. So this is my generalized formula. So we can use this formula. This is also a complicated formula, but we can just use it. It will be simplified if we find out alpha first and then just substitute this differences and this alpha values. You can get the interpolating polynomial. Is it clear? Any confusions? Anyone?
No, sir.
Okay. So this is my Newton's interpolation formula, right? So this is Newton's interpolation formula. So now we see an example, a numerical, then we move into the next topic. We will see two examples here, then we'll see the math. Okay, before we see the example, what we can do is we can see the matrix approach. Okay, suppose 1 second. Okay, using the matrix approach, how we can find out these coefficients. So first you have a set of data, say four data are there, y1, four set of data are there, x1, y1, x2, y2, x3, y3, and your x4, y. So if four data are there, we can fit a cubic polynomial. There is a polynomial of degree 3. So whatever number of data points are there, one less, right? A degree of one less than that, we can fit. So what was our equation? So if I write the equation, it will be a naught plus a1 x1 a1x plus a2 x square plus a3 x cube. So we have this equation. So if we use the previous Newton's interpolation formula, we can find out we can make a table. I will show that how to do that. Then we can find out the differences. We can use the formula to find out the coefficients a0, a1, a2, a3, and then we can find out the formula. So what we do in the matrix approach, we have four set of data, right? So in this equation, if we just substitute this, it is a0, a1 x1, a2 x1 square plus a3 x1 cube. Again, if we substitute the second one, it is a0, a1 x2, x2 square, a3 x2 cube. Y3 will be equal to a0, a1 x3, x2 square plus a3 x3 cube. Similarly, y4 will be a0, a1 x4, a2 x4 square, a3 x4 cube. So if we try to write this equation in a matrix form, what will be the matrix? So your right hand side matrix y1, y2, y3. So this will be 1, x1, x1 square, x1 cube, 1, x2, x2 square, x2 cube, 1, x3, x3 square, x3 cube, 1, x4, x4 square, x4 cube. Then we have your a0, a1, a2, and a3. So you can see this is my set of equations, and from this I have formed these are the four sets of equation, and from this I have formed this matrix. So here you know your Y matrix, this is your X matrix, this is your A matrix. So you need to find out A, right? So A is basically X inverse into Y. So using this, you can find out the coefficient of the interpolating polynomial. A is equal to X inverse into Y. So X is basically the values of the independent variable here. So there are four variables, so we can fit a polynomial of degree 3 at most. So I hope this is clear to you. Now we will see one problem. Just give me 5 minutes, I'll come back. Oh, people have left. Maruf, you are there?
Yes, sir.
Okay. Okay, so this was using the matrix approach, and now we have, I'll show you one example of solving this, and then we'll move to Lagrange polynomial. So one numerical example. So one second. You have a set of x and y's. It's 1, 2, 3, 4. Then we have 7, 17, 53, and 157. Then what we need here is we'll be using the Newton's difference formula, right? So we need the divided the differences. So delta yi here. So if we take these two, so what is delta y naught? Delta y naught is y1 minus y naught upon delta x. So delta y, sorry. So delta y naught is the difference between y1 and y naught. So it is 10 here. Using these two, I have delta y1 which is equal to 36. Using these two, we have delta y2 which is equal to 104. Similarly, we can find out del square y naught using these two and using these two. Sorry, del square y naught is 26. Del square y1 is how much? 64, 68. And del cube yi is difference between these two. So del cube y naught is 42, 42, right? Yes. So now, so what was my formula? It was this, right? So for this we need alpha. So what is alpha? Alpha is x minus x naught upon delta x. So it is x minus x naught here is 1 upon delta x is 1. So alpha is basically x minus 1. Okay. So now we substitute here P3 of alpha equal to y naught plus alpha delta y naught plus alpha into alpha minus 1 into del square y naught upon 2 factorial plus alpha into alpha minus 1. I think I've done one mistake here. Yes, these terms won't be there because I already absorbed them. Alpha into alpha minus 1 into alpha minus 2 into del cube y naught by 3 factorial. Okay. So we'll first find in terms of alpha, then at last we'll substitute this alpha. So what is y naught? Y naught is the first value of y, which is 7, plus delta y naught is 10, 10 alpha. Alpha into alpha minus 1 into del square y naught, which is 26 by 2, plus alpha alpha minus 1 alpha minus 2, del cube y naught is 42 by 6. So it is basically 7 plus 10 alpha plus 13 into alpha, 13 alpha into alpha minus 1 plus 7 alpha alpha minus 1 alpha minus 2. So this is in terms of alpha. So as we found out, alpha is equal to x minus x naught upon delta x. So alpha is here x minus 1. Therefore, your P3 of x, now this alpha we will substitute here, 10 into x minus 1, 13 into x minus 1 into x minus 2, plus 7 x minus 1 minus 2 x minus 3. If now we have to simplify this. 7 plus 10x minus 10, 13 x square minus 39x plus 26 into square minus 5x plus 6. So if you simplify this one, it will be 7x cube minus 29x square 8x minus 90. So this is your P3 of x. So this is the polynomial equation of the third degree polynomial that represents your data. This is obtained using the Newton's interpolation formula. I hope it is clear to you. So if it is clear, then now we'll move to the Lagrange's interpolating polynomial. We have two more topics, the Lagrange's interpolating polynomial and the Newton's divided difference for today. So this was one interpolating polynomial formula, which was Newton's interpolating polynomial. So now we have the what is called the Lagrange interpolating formula. So here basically we represent this the dependent variable as summation of I equals to 1 to n is the number of data, li of x into y of xi. So here this li of x is the Lagrange coefficient. So what is this li of x? Li of x is the product which is given by pi for j not equals to I x minus xj upon xi minus xj. This is your Lagrange's interpolating formula. So if we just substitute here summation, if we substitute this expression for Li of x, it will be a summation I equals to 1 to n. Then we have product pi, which is j not equals to I x minus xj upon xi minus xj into y of xi. So this is the complete formula of my Lagrange interpolating polynomial. But from this it is not at all clear how we expand. We'll expand this formula and we'll see how it is. So for that, first we need to find out what is, if we first using this first equation, okay, just the first equation is simpler, right? From the first equation, if we try to find out what is y, we can find out it is L1 of x into y of x1 plus L2 of x into y of x2 like this, right? Up to Ln of x into y of x. So here your y of x1, y of x2, these are the values of the independent variable, right? So this is known to you. So you need to find out and concentrate on L1, L2, L3 up to Ln, right? So now we try to find out what is L1 of x from this second equation. So I is here. So here we can see it. If I just simplify this one, so I is here 1. So it is basically j not equals to 1, x minus xj upon x1 minus xj. So your j will vary from 1 to n, but j will not be equal to the I. That is j not equals to 1. So here, since it is L1, j will not be equal to 1. So it will start from 2. So it is basically x minus x2 upon x1 minus x2 into x minus x3 upon x1 minus x3 into x minus x4 upon x1 minus x4. Like this it will continue up to x minus xn upon x1 minus x. Similarly, what will be L2 of x? So you can see here in L1 of x, the numerator has all the terms except x1. Okay, and this term here, it will be x1. So similarly, if we just expand L2 of x, it will be x minus x1. x2 will not be there. It is x minus x3, x minus xn upon x2 minus x1, x2 minus x3, dot 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 x2 minus xn. So this is the, if we just substitute in place of L1 and L2, if we expand, you will get this. So finally, what is my fx? That is the polynomial. What was it? L1 of x into y of x1, L2 of x, y of x2, ln of x, y of xn. right? So if we substitute here L1 of x, it is x minus x2, x minus x3, dot x minus xn upon x1 minus x2, x1 minus x3, dot x1 minus xn multiplied by y of x1. Similarly, I'm not writing the other terms. The final term I'm writing. So it will be like this, okay? It will continue like this. This is the first term, then the second term, it will continue like this. I hope it is clear to you. I'll give an example to understand how we'll be finding out this. Suppose you have x data, y data, right? X you have 5, 10, 15, 20, and this you have 10, 55, 92, 120. So if you want to find out the Lagrange interpolating formula for polynomial here, first you need to, I'm not doing it, I'll just show you. So what is L1 of x? X minus x2, x minus x3. So here there are four terms. So x minus x4 upon x1 minus x2, x1 minus x3, x1 minus x4. So it is x minus 10 into x minus 15, x minus 20 upon x1 minus x2 is minus 5, minus 10, minus 15. Minus 5 into minus 10 into minus 15. So 5 tens are 50, 1 by 7, 50. Minus. So this will be my L1 of x. Similarly, what will be my L2 of x? You have to find out x minus x1, x minus x3, x minus x4 upon x2 minus x1, x2 minus x3, x2 minus x4. It is basically x minus 5, x minus 10, sorry, x minus 15, x minus 20, x2 minus x1 is 5, right? 5 minus 5 and minus 10. 5 tens are 50. 5 minus 5, 10. So it is 250. Like this, you have to find out L3 of x and L4 of x, and then you have to substitute all this in the in this polynomial formula. Y of x1 is your 10, y of x2 is 55, y of x3 is 92, and y of x4 is 120. So for this, the MATLAB codes I'll show you in the next class. Today we will just complete the theory part, and next class we'll show the MATLAB code. So there is one more concept here, one more polynomial, which is called the Newton's divided difference formula. Newton's divided difference. I'll just show the concept here. Is similarly similar kind of concept here also. So we have xi and yi, say x1, x2, x3, and x4. Similarly, we have y1, y2, y3, and y4. So first order divided difference. Okay, first order divided difference is between these two. We represent the divided difference like this. So y of 2 comma 1, this 2 is y of 3 comma 2, this 2 is y of 4 comma 3. The first order. Then you have the second order between these two and these two. Y of 3 2 1 and y of 4 3 1 4 3 2. Third order you have this one, y of 4 3 2 1. So what are these? Y of 2 1 3 2. What is the formula for this? So y of 2 1, that is the first order difference. It is y2 minus y1 upon x2 minus x1. Similarly, y of 3 2 is y3 minus y2 upon x3 minus x2. Y of 4 3 is basically y4 minus y3 upon x4 minus x3. Similarly, if we try to find out the second order differences, y of 3, 2, 1, it is y of 3 comma 2 minus y of 2 comma 1 upon x3 minus x1. Similarly, y of 4 comma 3 comma 2, it is y of 4 comma 3 minus y of 3. It's very easy to remember, upon x4 minus x2. Similarly, you can get the other one also. The third order, y of 4, 3, 2, 1 is basically y of 4, 3, 2 minus, 1 second, minus y of 3, 2, 1 upon x4 minus x1. So once you get this, all these coefficients, then you have to form your actual interpolating polynomial, which is y1 plus x minus x1 into first order divided difference y21 plus x minus x1 into x minus x2 y of 3, 2, 1 plus x minus x1 x2 x minus x3 multiplied by the third order difference 4, 3, 2. So this is just a mathematical concept here. We are using why we are telling it as divided difference, because unlike the Newton's interpolation formula, what difference we were using there, we are just taking the difference between the consecutive y values, and we were not dividing it by anything. So here we are basically dividing it with the corresponding x difference of the x values also. That's why we are calling it as divided differences. So if there are four x values, four set of data, so we'll have up to third order differences. If you have n set of data, you'll have up to n minus 1 order differences, and accordingly we can find out, and we can find out the interpolating polynomial for this. I hope it is clear to you. Any questions? Anyone? Mustafa, Maruf, anyone?
Yes, sir. It is clear.
Okay, it is clear, right? No questions? Okay, fine. Okay, then we'll meet in the next class on next Friday from 6:30. Thank you. Thank you for attending the class. You can leave.
Yes, sir. Thank you, sir.
Thank you, sir.
Thank you.